You think you understand why water freezes. Everyone does. You put water in the freezer. It gets cold. It turns to ice. Simple. Temperature drops, water freezes. That's the explanation you learned. That's what everyone says. But here's the problem with that explanation. It doesn't actually explain anything. It just describes what happens. Saying water freezes because it gets cold is like saying a car moves because you press the gas pedal. You're describing the trigger, not the mechanism. You're naming the phenomenon, not understanding it. So let me ask you directly, what is actually happening when water freezes? Not what you do to make it happen. What is happening at the level of atoms and molecules? What forces are at work? What changes? And why does that change produce the specific thing we call ice? Most people have never really thought about this. They accept freezing as a basic fact. Water gets cold enough, it becomes solid. End of story. But that's not understanding. That's just familiarity masking ignorance. And when you actually look at what's happening, when you trace the process down to the atomic level, you discover something far more profound than temperature change. You discover that freezing is the universe imposing order, that it's the same fundamental forces that hold your body together, suddenly switching from allowing chaos to demanding structure. That the simple act of water turning to ice is a window into how reality itself is organized. Let's start with what water actually is, not the substance you drink. The molecular structure. Water is H2O, two hydrogen atoms bonded to one oxygen atom. The shape matters. It's not a straight line. The two hydrogen atoms stick out at an angle, about 104.5 degrees from each other. This bent shape is not arbitrary. It's a consequence of how electrons arrange themselves around the oxygen atom, following rules dictated by quantum mechanics. Now, in liquid water, these molecules are moving constantly. They're not sitting still. They're vibrating, rotating, sliding past each other. And here's what you need to understand about this motion. This motion is not optional. It's not that the molecules choose to move. Motion is what temperature is. Temperature is not a substance. It's not a thing that makes molecules hot. Temperature is a measure of how fast molecules are moving. More precisely, it's a measure of their kinetic energy, their energy of motion. When water is warm, the molecules are moving fast. They're jiggling violently. They're bouncing off each other with high energy. When water is cool, the molecules are moving slower. They're still moving, but less frantically. And here's the critical point. As long as the molecules are moving fast enough, they can't settle into any fixed arrangement. They slam into each other, bounce away, collide with others, never staying in one configuration for more than an instant. The thermal motion, the random kinetic energy, prevents any stable structure from forming. But the molecules want to form a structure, or rather the forces between them would produce a structure if the motion would let them, because water molecules are not neutral. They have a slight electric charge distribution. The oxygen end is slightly negative. The hydrogen ends are slightly positive. This is called a polar molecule. And polar molecules attract each other. The positive end of one molecule is drawn toward the negative end of another. This attraction is not metaphorical. It's not like magnets where we don't really know what's happening. This is electromagnetic force, the same force that holds atoms together, the same force that makes chemistry possible, the same force that prevents your hand from passing through a table, one of the four fundamental forces of the universe. And it's acting between water molecules constantly, trying to pull them into specific orientations, specific arrangements where positive aligns with negative. In liquid water, this attraction is present but frustrated. The molecules are moving too fast. They get pulled toward each other. They orient briefly in favorable positions, but then the thermal motion kicks them apart again. The electromagnetic attraction and the kinetic energy are competing. The attraction wants order. The motion creates chaos. And in liquid water, at temperatures above freezing, the motion wins. The molecules remain disordered, sliding and tumbling past each other in a constantly shifting arrangement. Now start cooling the water. Lower the temperature. What are you actually doing? You're not adding coldness. Cold is not a substance. You're removing energy. You're letting the water transfer its thermal energy to the surrounding environment, the air in the freezer, the metal of the container, whatever is colder than the water. Energy flows from hot to cold, always. That's the second law of thermodynamics. Heat flows spontaneously from higher temperature to lower temperature until equilibrium is reached. As energy leaves the water, the molecules slow down. Their kinetic energy decreases. They're still moving, still bouncing around, but less violently. And as they slow, something becomes possible. The electromagnetic forces between molecules, The forces that were always there suddenly become relatively stronger, not because the forces themselves change. They don't. The electromagnetic attraction between two water molecules is the same at any temperature. What changes is the kinetic energy opposing that attraction. Think of it this way. You have a ball rolling around inside a bowl. If the ball is moving fast, it rolls up the sides, it moves all over, it never settles. But if you slow the ball down, it eventually rolls to the bottom of the bowl and stays there. The shape of the bowl didn't change. The gravitational pull toward the bottom was always there, but the ball's motion prevented it from settling. Only when the motion slowed did the shape of the bowl, the gravitational potential, determine the ball's position. Water molecules are the ball. The electromagnetic forces between them create a potential energy landscape, a shape that favors certain arrangements, and the thermal motion is the ball's speed. When the temperature is high, the motion overwhelms the landscape. When the temperature drops, the landscape starts to matter. At a certain temperature, 0 degrees Celsius, at standard pressure, something critical happens. The kinetic energy of the molecules drops below a threshold. The thermal motion is no longer sufficient to overcome the electromagnetic forces, pulling molecules into specific orientations. And suddenly, the molecules can lock into position. They can form stable arrangements where each molecule is surrounded by others in a specific geometric pattern. This is what freezing is. It's not molecules stopping their motion. They never stop. Even in ice at absolute zero, quantum mechanics requires some residual motion. Freezing is molecules transitioning from a disordered, chaotic arrangement to an ordered, structured arrangement, from liquid to crystal, from randomness to geometry. And the geometry matters. When water freezes, each water molecule forms hydrogen bonds with 4 neighboring molecules. These bonds are not true chemical bonds. They're weaker, more like strong attractions, but they're specific. The angle at which hydrogen bonds form is determined by the electron distribution in the water molecule. And that angle, combined with the tetrahedral arrangement of bonds around each molecule, forces the molecules into a particular structure. That structure is hexagonal. In ice, water molecules arrange themselves in a hexagonal lattice. Each molecule is at the center of a tetrahedron, bonded to 4 others, and these tetrahedra connect in a way that creates hexagonal rings when viewed from above. This is why snowflakes have 6-fold symmetry. It's not a coincidence. It's not aesthetic. It's the direct consequence of the molecular structure of ice. The geometry of the crystal is dictated by the geometry of the molecule and the nature of the electromagnetic forces between them. Here's something that should break your intuition. Ice is less dense than liquid water. Most substances, when they freeze, become denser. The molecules pack closer together in the solid state, but water does the opposite. Ice floats. Everyone knows this. But why? Because the hexagonal crystal structure of ice has empty space. The molecules are locked into a rigid geometric arrangement that leaves gaps. In liquid water, the molecules are disordered, and in that chaos, they can pack more closely. They can fill space more efficiently. But in ice, the rigid structure, the specific angles of the hydrogen bonds, force the molecules apart into a more open lattice. The order creates space. The structure is less efficient at filling volume than the random arrangement of the liquid. Think about the consequences of this. If ice were denser than water, it would sink. Lakes and oceans would freeze from the bottom up. Aquatic life would die. Ecosystems would collapse. Earth's climate would be unrecognizable. The fact that ice floats is not a trivial detail. It's a consequence of molecular geometry that fundamentally shapes the habitability of this planet. Now let's go deeper. Why do hydrogen bonds form at specific angles? Why does the electromagnetic force between water molecules create this particular structure and not some other structure? The answer takes you into quantum mechanics. The electrons in the oxygen atom don't orbit like planets. They occupy regions of space described by probability distributions, by wave functions. These regions have shapes. The orbitals that participate in bonding with hydrogen have a specific angular distribution. This forces the hydrogen atoms to stick out at an angle, not in a straight line. And this angle, this geometric constraint imposed by quantum mechanics, determines how water molecules can pack together. The structure of ice, the reason your freezer produces solid cubes and not some amorphous frozen liquid, traces back to the behavior of electrons in atoms, to the solutions of the Schrödinger equation for the water molecule, to the fundamental laws of quantum mechanics. What looks like a simple kitchen phenomenon is the macroscopic expression of quantum mechanical rules operating at the atomic scale. Let's talk about what you're actually feeling when you hold ice. You think you're feeling coldness, but cold is not a thing. Cold is the absence of heat, which is the absence of molecular motion. When you hold ice, heat flows from your hand into the ice. The fast-moving molecules in your skin collide with the slower-moving molecules in the ice. Energy transfers. Your hand loses kinetic energy. The ice gains it, and your nerve endings detect this energy loss as the sensation of cold. But here's what you're not feeling. You're not feeling the molecules themselves. You've never touched a molecule. Your hand never makes contact with the ice at the molecular level. There's always a gap. The electrons in your skin and the electrons in the ice repel each other with enormous electromagnetic force. What you feel is the hardness of ice. The resistance when you press on it, that's electromagnetic repulsion. The same fundamental force that creates the hydrogen bonds in ice is also preventing your hand from passing through it. Every sensation you've ever had of touch, every feeling of solid matter, is electromagnetic force acting at a distance. There is no contact. There is only force. And the reason ice feels hard, the reason it resists pressure, is because the molecules are locked in a crystal lattice. They can't easily move out of position. The structure is rigid. In liquid water, molecules can slide past each other. Push on water, it flows. Push on ice, it pushes back. Not because ice is fundamentally different substance, but because the arrangement is different. Order resists deformation in a way that disorder does not. Now, here's something that will disturb you. The freezing process is not deterministic in the way you think. Water does not freeze uniformly at exactly 0 degrees Celsius everywhere at once. Freezing begins at nucleation sites, impurities, rough surfaces, tiny dust particles, places where the first few molecules can begin to lock into the crystal structure. And once a small crystal forms, it grows. Surrounding molecules align with the existing structure. The crystal propagates outward from the nucleation site. This is why supercooled water exists. You can cool pure water below 0 degrees Celsius without it freezing if there are no nucleation sites. The water is unstable. It wants to freeze. The temperature is low enough, but it needs a trigger, a disturbance, a surface. And when you provide that trigger, when you tap the container or drop in a crystal of ice, the entire volume freezes almost instantaneously. The molecules were ready. They were on the edge. They just needed a template, a starting point. What this tells you is that freezing is not just about temperature. It's about structure formation. It's about overcoming an energy barrier. The molecules in supercooled water are moving slowly enough to lock into a crystal, but they haven't found the right configuration to start. It's like a room full of people who could form a line, but no one wants to be first. Once one person stands in position, everyone else quickly follows. The first step is the hardest. After that, the structure propagates naturally. This is phase transition, the shift from liquid to solid. And phase transitions are abrupt. They don't happen gradually. You don't get something that's half liquid and half solid at the molecular level. At any given point, the molecules are either in the disordered liquid state or the ordered crystal state. There's no intermediate. The transition is discrete. One moment, a molecule is free to move. The next, it's locked in place. And this happens to billions of molecules nearly simultaneously as the crystal front moves through the water. Think about the scale of this. In a single ice cube, there are roughly 10 to the 24 water molecules. A trillion, each one made of 3 atoms, each atom made of electrons, and a nucleus, each nucleus made of protons and neutrons. And every single one of these molecules, in the span of seconds, transitions from chaotic motion to precise geometric arrangement. The organization is perfect, every molecule in its place, every angle correct, the entire crystal structure consistent throughout. How does this happen? Not through conscious coordination, not through planning, through local interactions. Each molecule responds to the electromagnetic forces from its immediate neighbors. Those forces have a preferred geometry. And when the thermal motion is low enough, the molecules fall into that geometry. The global structure, the macroscopic ice crystal, emerges from countless local interactions, order from simple rules applied at the molecular level. This is how complexity arises in nature, not from top-down design, from bottom-up assembly. The universe has fundamental forces. Those forces have specific mathematical forms, and when matter obeys those forces, structure emerges. Atoms combine into molecules. Molecules organize into crystals. Crystals grow into patterns. Patterns create form. And all of it is the inevitable consequence of particles following rules. Here's where it connects to everything else. The electromagnetic force that makes water freeze is the same force that holds atoms together. It's the same force that makes chemistry possible. Every reaction, every bond formation, every molecular interaction in your body is electromagnetic. The proteins that build your cells, the DNA that encodes your genes, the signals in your neurons, all electromagnetic, all following the same fundamental principles that make ice form in your freezer. And those principles are not arbitrary, they're consequences of deeper laws. Quantum mechanics dictates how electrons behave. Special relativity combines with quantum mechanics to produce quantum electrodynamics, the theory of how charged particles interact. The structure of ice is not an isolated fact. It's a specific manifestation of general principles that govern all of matter. When you see ice form, you're watching quantum mechanics in action. You're seeing symmetry principles expressed in crystalline geometry. You're observing entropy decrease locally as energy flows outward. You're witnessing the universe's preference for minimum energy configurations. What looks simple is profound. What seems mundane is universal. Now let's make this even more precise. When ice forms, something measurable changes. The entropy decreases. Entropy is a measure of disorder, of the number of possible arrangements a system can have. In liquid water, the molecules can be arranged in countless ways. Every configuration is different. Every moment the arrangement changes. The entropy is high. In ice, the molecules must be in specific positions. The number of allowed arrangements drops dramatically. The entropy is lower. But here's what students get wrong. They think entropy always increases. That's the second law of thermodynamics. Entropy of a closed system increases over time, but ice has lower entropy than liquid water. How is that possible? Because the ice is not a closed system. When water freezes, it releases energy. Heat flows out. That heat goes into the surroundings. The air warms. The freezer works harder. The environment gains entropy, and the entropy gained by the environment is greater than the entropy lost by the water. The total entropy increases. Locally, order forms. Globally, disorder spreads. This is not a violation of the second law. This is the second law working exactly as it must. The energy released when water freezes is called latent heat, specifically the latent heat of fusion. It's 334 joules per gram. That's not a small amount. When 1 kilogram of water freezes, it releases 334,000 joules of energy. That energy has to go somewhere. It flows into whatever is colder than the freezing water, and that energy represents the difference between the disordered liquid state and the ordered solid state. Why does freezing release energy? Because the crystal structure is lower energy. The hydrogen bonds in ice are in their optimal configuration. The molecules are arranged in the geometry that minimizes potential energy. In liquid water, the molecules are constantly moving through higher energy configurations. They're being forced into non-optimal arrangements by thermal motion. When they lock into the crystal, they settle into the energy minimum, and the difference gets released as heat. Here's the thing that makes this profound. Energy and structure are connected. High energy means freedom, disorder, motion. Low energy means constraint, order, stillness. The universe prefers low energy. Systems naturally evolve toward minimum energy states if you let them, but they can only get there if they can shed the excess energy. That's why you need cooling. You need to remove energy from the water. You need to let it reach that lower energy crystal state. And here's where it gets strange. At the moment of freezing, at exactly 0 degrees Celsius, liquid water and ice can coexist. You can have both phases present simultaneously. They're in equilibrium. The energy to freeze one more molecule equals the energy to melt one. Add heat, some ice melts. Remove heat, some water freezes. The system balances precisely at the phase boundary. This is not an approximation. This is exact. At standard pressure, pure water freezes at 273.15 Kelvin. Not 273.14, not 273.16, exactly 273.15. This is a fixed point. It's so precise that the Celsius scale is defined by it. 0 degrees Celsius is defined as the freezing point of water at standard pressure. The sharpness of this transition, the exactness of the temperature, tells you something important. Phase transitions are not gradual, they're abrupt. They happen at specific conditions. Cross that threshold, everything changes. And here's the final thing you need to understand. Freezing is not just about water. Every liquid that freezes does so through the same general process. The specific structure differs, the temperature differs, but the mechanism is always the same. Lower the temperature, reduce the kinetic energy, allow the intermolecular forces to dominate. Let the molecules lock into their preferred arrangement, liquid to solid, disorder to order, chaos to structure. The universe is full of transitions like this. Stars condense from gas clouds, crystals grow from solutions, life assembles from molecules. Every case involves the same pattern. Energy decreases, structure increases, local order forms at the expense of spreading disorder elsewhere, and it all traces back to fundamental forces and the statistical behavior of vast numbers of particles following simple rules. So what is freezing really? It's not water getting cold, it's the electromagnetic force overwhelming thermal motion. It's quantum mechanics determining molecular geometry. It's entropy and enthalpy competing, with enthalpy winning at low temperatures. It's a phase transition driven by energy minimization. It's the universe building order from the bottom up. And it's happening in your freezer right now every time you make ice, not because of some magical property of cold, but because the laws of physics are what they are. And those laws, given the right conditions, produce structure. Always, inevitably, perfectly. Reality does not care that this seems too complicated to be happening in something as ordinary as ice. Reality is what it is. And what it is, at the most fundamental level, is far stranger and more beautiful than the simple story we tell ourselves about water and cold.